Look up at the night sky. Every point of light you see is a massive nuclear furnace, burning through millions of tons of fuel every single second. We live in a universe filled with light, a period cosmologists call the Stelliferous Era, but this era is not permanent. It is a fleeting moment in the grand timeline of the cosmos. Every star you see tonight is destined to fail, and eventually, the universe will go dark. To understand the end of light, we must first understand how stars live and die. A star is a delicate balancing act between two immense forces. Gravity pulls matter inward, trying to crush the star into a single point. In opposition, the nuclear fusion at the core pushes outward, releasing tremendous energy. As long as a star has hydrogen to fuse into helium, this balance holds, but fuel is finite. Our own sun is a yellow dwarf star, located about 150 million kilometers or 93 million miles from Earth. It has been burning for 4.5 billion years, and it has enough fuel to last for another 5 billion years. When its hydrogen runs out, the core will collapse, and the outer layers will expand, transforming our sun into a red giant. Eventually, it will shed its outer layers, leaving behind a dense, glowing core known as a white dwarf. Massive stars, those many times larger than our sun, burn through their fuel much faster. They live for only a few million years before ending their lives in violent supernova explosions. These explosions seed the universe with heavy elements, but they also mark the rapid death of the most brilliant lights in the cosmos. The brightest stars are the first to die. The true survivors of the universe are the red dwarfs. These are the smallest, coolest, and most common stars in existence. A typical red dwarf has only a fraction of the mass of our sun. Because they are so small, the pressure and temperature at their cores are much lower. This means they fuse hydrogen into helium at an incredibly slow rate. Furthermore, red dwarfs are fully convective. In a star like our sun, the helium produced in the core stays in the core, but in a red dwarf, the plasma constantly circulates. Fresh hydrogen from the outer layers is pulled down into the core, while the helium ash is pushed outward. This allows a red dwarf to use almost 100% of its hydrogen supply. Because of this extreme efficiency, a red dwarf can burn for trillions of years. To put that into perspective, the universe itself is only about 13.8 billion years old. Not a single red dwarf has ever died in the entire history of the cosmos. They are the ultimate marathon runners of the stellar world. The closest star to our solar system is a red dwarf named Proxima Centauri, located 4.24 light-years. It will continue to burn long after our sun has faded into a cold ember. But even trillions of years will eventually pass. As we look deep into the future, the universe is changing. Dark energy, a mysterious force that permeates all of space, is accelerating the expansion of the universe. Galaxies are being pushed apart at staggering speeds, reaching millions of kilometers or millions of miles per hour. The observable universe currently spans 93 billion light-years. Over the next 100 billion years, this expansion will have a profound effect on the night sky. The space between galaxy clusters will stretch so much that light from distant galaxies will no longer be able to reach us. The cosmic horizon will shrink. If intelligent life exists in that distant future, they will look up and see only the stars of their own galaxy. The rest of the universe will have faded into an impenetrable black void. As the eons roll on, the star-forming gas within galaxies will be depleted. Nebulae, the great stellar nurseries, will dissipate. Without new gas, no new stars can be born. The universe will enter a long, slow decline. The massive stars will be long gone. The sun-like stars will have faded into white dwarfs. Only the red dwarfs will remain, glowing faintly in an increasingly empty cosmos. Imagine a time 1 trillion years from now the Milky Way has merged with the Andromeda galaxy, forming a massive elliptical galaxy. The brilliant spiral arms are gone. The sky is dominated by the dim reddish glow of ancient stars. The universe is growing colder, quieter, and darker. As a red dwarf finally approaches the end of its life, something unusual happens. Unlike our sun, it will not expand into a red giant. Instead, As its hydrogen runs low, the star will actually grow hotter and more luminous. It will transition into a theoretical object known as a blue dwarf. This phase will last for a few billion years, a final defiant burst of energy before the end. Once the last of the hydrogen is fused, the blue dwarf will collapse under its own gravity. It will become a white dwarf, a sphere of degenerate matter roughly the size of Earth, but containing half the mass of a star. This white dwarf will have no source of internal energy. It will simply radiate its residual heat into the freezing vacuum of space. To understand the physics of a white dwarf, we must look at quantum mechanics. When the nuclear fusion stops, gravity tries to crush the star. However, the electrons within the stellar core are squeezed so tightly together that they resist further compression. This phenomenon is known as electron degeneracy pressure. It is the only force preventing the dead star from collapsing into a black hole. A single teaspoon of this degenerate matter would weigh several tons on Earth. This incredibly dense material is highly conductive, meaning the core of a white dwarf is essentially a single massive crystal of carbon and oxygen, slowly radiating its thermal energy away. This process of cooling takes an unimaginably long time. A white dwarf will slowly fade from white to yellow to red and finally to black. It will become a black dwarf, a cold, dead remnant of a once shining star. The universe will be littered with these invisible corpses, drifting silently through the dark. When the very last red dwarf burns out, the universe will cross a critical threshold. It will leave the Stelliferous Era and enter the Degenerate Era. The cosmos will be populated only by black dwarfs, neutron stars, and black holes. The era of starlight will be officially over. In this dark future, the temperature of the universe will continue to plummet. The current temperature of the cosmic microwave background is 2.7 Kelvin or minus 454 degrees Fahrenheit. As the universe expands, the wavelength of these background photons is stretched. This stretching process, known as cosmological redshift, drains the photons of their energy. Trillions of years from now, these wavelengths will be stretched to the size of entire galaxies, rendering them completely undetectable. The ambient temperature of space will approach absolute zero, reaching nearly 0 Kelvin or minus 459 degrees Fahrenheit. It will be a permanent frozen night. At this temperature, atomic motion practically ceases. The universe will be locked in a state of thermodynamic equilibrium, where no work can be done and no life can exist. Without the energy provided by stars, planets will freeze solid. Atmospheres will collapse and fall as snow onto barren, icy surfaces. Any surviving planetary systems will be dark, cold, and completely inhospitable to life as we know it. The universe will have achieved a state of maximum entropy, a vast, silent graveyard. Occasionally, in this pitch-black void, two black dwarfs might collide. This rare event could trigger a brief, violent supernova, lighting up the darkness for a few fleeting weeks. But these flashes will be temporary anomalies. They will quickly fade, returning the universe to its eternal slumber. Eventually, even the degenerate matter will begin to decay. Protons, the building blocks of atoms, may have a finite lifespan. If proton decay occurs, the black dwarfs and neutron stars will slowly dissolve into radiation and subatomic particles. The only macroscopic objects left in the universe will be black holes. This will mark the beginning of the black hole era. But even black holes are not eternal. Through a process called Hawking radiation, they slowly leak mass and energy back into space. Over timescales that defy human comprehension, even the supermassive black holes at the centers of galaxies will evaporate, ending their lives in brilliant flashes of gamma rays. After the last black hole evaporates, the universe will enter the dark era. It will be a sea of photons, neutrinos, and scattered electrons, all drifting further and further apart. The universe will be cold, dark, and empty, expanding forever into the void. This is the ultimate fate of the cosmos. It is a sobering thought, a reminder of the impermanence of all things, but it also highlights the incredible rarity and beauty of the present moment. We exist in the Stelliferous Era, a time of light, warmth, and complexity. Every time you look at the stars, you are witnessing a temporary miracle. The nuclear fires burning across the galaxy are a finite resource, a cosmic spark that will eventually fade. We are the lucky observers, born at the exact right time to witness the universe in all its shining glory. The last star will burn out, and the universe will go dark. But until that day comes, trillions of years from now, the cosmos will continue to shine. We must appreciate the light while we have it, for it is the very thing that makes our existence possible. The story of the universe is a story of light and dark, and we are privileged to be a part of it. Thank you for watching. I really would appreciate it if you would subscribe, follow, like, and comment, as this helps the algorithm know that people are interested in my videos.